And I'm very happy to have as our speaker today, Daisuke Kishimoto from Kyoto University, and he will speak on Tverberg's theorem for cell complexes. Daisuke, take it away. Share your screen.
Thank you. Okay, thank you for the introduction. And I would like to thank the organizers for this chance of talk. But before I begin, I have to apologize that I'm not going to talk about TC, but some of the ingredients of my talk will be important or interesting in applied topology. Okay, so the title of my talk is Tverberg's theorem for cell complexes, and this is joint work with Sho Hasui, Masahiro Takeda, and Mitsunobu Tsutai. Okay, so let's start with recalling Tverberg's theorem. And we start with a very naive problem, points in a plane. Okay, suppose you have 3 endpoints in a plane. Then these points, these 3 endpoints determine n triangles which have a point in common. For example, if you have 6 points like this, then of course you can make a triangle like this, but this is a bad choice of triangles because they don't have point in common. But the theorem guarantees that you always have a good choice. For example, if you choose triangles like this, then you have points in common here. Right. So this theorem is due to Birch, who proved this theorem in 1959, so very old theorem. Okay, so let's move to a better result. I mean, if we replace triangles with convex halves, then we get a sharper result. Okay, so suppose you have 3n minus 2 points in a plane. Then you can divide these points into n subsets whose convex halves have a point in common. Right. So this is sharper than the former results because we have 3n minus 2 points in a plane. And actually, the number 3n minus 2 is best possible. For example, 3n minus 3 for n being 2 does not work. I mean, if you have 3 points in a plane, then essentially there is one partition of these 3 points into 2 subsets like this. And these partitions doesn't give you any point in common because they are disjoint. Okay, so this is a story about a point in a plane. So we can ask what happens if we have point in R to the D. And of course, there are some results. There are some answers to these questions. And the first one is due to radon, and which states that if you have D plus 2 points in RD, then you can divide them into 2 subsets whose convex halves have a point in common. Okay, so you may think that the number of points are too small because it's D plus 2. just two more than the dimension of the Euclidean space. So you can ask what happens if you have more points in R2D. And the answer is the Tverberg's theorem. And suppose you have D plus 1 times R minus 1 plus 1 points in RD, then you can divide them into R subsets whose convex halves have a point in common. And actually, the number D plus 1 times R minus 1 plus 1 is best possible. Okay, so this is purely a combinatorial theorem. So, but I want to connect this theorem to topology. So I have to translate this theorem into some topological setting. Right. So to this end, let's consider a affine map. I mean, if you have D plus 1 times R minus 1 plus 1 points in RD, then you can get an affine map from D plus 1 times R minus 1 simplex into RD, such that each convex house of points is the image of the corresponding face. So we can translate Tverberg's theorem like this. For any affine map F from D plus 1 times R minus 1 simplex into RD, there are pairwise disjoint faces sigma 1, sigma R, such that their image by F intersect. Okay. So now we translate Tverberg's theorem in terms of the affine map. So it is, so the naive question arises like this: what happens if we replace an affine map by a continuous map? And this is somewhat a silly question because affine maps and continuous maps are very far. So it doesn't seem that we can generalize Tverberg's theorem for a continuous map, but it's possible. And the result is called the topological Tverberg's theorem, and which was first proved in 81 and generalized in 87 and 96. Okay, so the statement is like this. For any continuous map, not affine map, F from D plus 1 times R minus 1 simplex into RD, there are pairwise disjoint faces, R disjoint faces sigma 1 to sigma R, such that their images by F intersect. The important point here is that we have to assume that R is a prime power. And this assumption seems somewhat technical things and doesn't seem essential. And people were believing that, but actually this assumption is necessary. I mean, if we remove this assumption, I mean, R being a prime power, then the theorem doesn't hold. So this is very, very interesting, and the proof is of independent interest because it uses practical calculation of the radon cohomology. But so the difference between the topological Tverberg's theorem and Tverberg's theorem is this assumption: R is a prime. Okay, so let me ask more questions. Oh, sorry, before asking my question, let me see some consequences. Okay, so if we take R to be 2, then we have this corollary. For any map, for any continuous map from D plus 1 simplex into RD, say F, there are pairwise disjoint faces sigma 1 and sigma 2, such that F sigma 1 and S sigma 2 intersects. And this is a topological version of the radon theorem, which I showed you before. This one. So the radon theorem holds even if we replace an affine map by a continuous map. So, okay, so let me excuse the choice of this, or my choice of this topic like this. So in the topological radon theorem, we consider a continuous map from D plus 1 simplex into RD. But we, and also we consider pairwise disjoint faces sigma 1 and sigma 2. So we don't need a map from D plus 1 whole of D plus 1 simplex. I mean, we only need a map from the boundary of the D plus 1 simplex into RD. And of course, the boundary of the D plus 1 simplex is homeomorphic with D sphere. So the topological radon theorem is about a map from SD into RD. And you know, theorem for this kind of map, it's Borsuk-Ulam theorem. Okay, so for any continuous map from F, for continuous map F from SD to RD, there is a point X in SD such that Fx coincides with F minus X. Of course, we are assuming that SD is the unit sphere in RD plus 1. So these antipodal points correspond to, if we consider these antipodal points correspond to disjoint faces in the boundary of the D plus 1 simplex, the topological radon theorem is a combinatorial counterpart of the Borsuk-Ulam theorem. And of course, there is a LS version of the Borsuk-Ulam theorem like this. For any open cover of SD by D plus 1 open sets, say UI, then there is UI such that UI and minus UI intersect. So I apologize that I'm not going to talk about TC, but there is a slight connection between these topics. So this is my excuse of my choice. All right, so let's go further on Tverberg's theorem. Okay, let me ask more questions about the theorem. We have already replaced the affine map by a continuous map in the Tverberg's theorem. And with some assumption on R, the theorem still holds for continuous maps. So I want to ask you, why are we still considering a simplex? This is a very naive and natural question. And actually, a kind of this question was asked Tverberg himself. He asked whether we can replace a simplex by a polytope, convex polytope. And the answer is yes. We can replace a simplex by a polytope in the topological Tverberg's theorem. But the reason for this answer is that the boundary of a polytope of any polytope is a refinement of the boundary of a simplex. So the answer is just a corollary of the topological Tverberg's theorem for a simplex. So this is not a good question. And in 2019, Ziegler and his collaborators constructed a family of matroids. It's a kind of simplicial complexes, infinite family, which are replaceable with a simplex in the topological Tverberg's theorem. But this is constructed by a very direct combinatorial way, and we don't have any other simplicial complex which are replaceable with a simplex. So we want more examples. This is my motivation to study this the Tverberg's theorem. Right. Okay, so let me show you the main theorem, which is the answer to this question. Okay, to state the main theorem, let me introduce some simplicial complexes, which are called RR complementary and acyclic. Okay, let's set notation. We take a regular CW complex X. Okay. And for faces sigma 1 to sigma k of this regular CW complex, face means the closed cell, closed, not open, closed cell. For these k faces, let kx of sigma 1 to sigma k be a subcomplex of X consisting of faces separated from sigma 1 to sigma k. So X is obtained by removing open stars of sigma 1 to sigma k from X. And as usual, we say that X is n-acyclic if its homology is isomorphic with a point in dimensions less than n. And for convenience, we say that a space is -1 acyclic if it's not empty. So with these notations and terminology, we define a new class of simplicial complexes. Okay, so let X be a regular CW complex as before. Then we say that X is an R complementary n-acyclic simplicial n-acyclic CW complex. If for any faces sigma 1 to sigma k satisfying this dimensional condition, then the subcomplex X of sigma 1 to sigma k is n minus dimension sigma 1 minus dimension sigma k acyclic. So the definition seems a little bit complicated, but if you examine some examples, you can easily find many examples satisfying these conditions. Okay, let me show you some examples. For example, a D simplex is R minus 1 complementary, D minus R acyclic. And this is a very simple example. And the important one is the next example. I mean, every simplicial D sphere is 1 complementary D minus 1 cyclic. So this is easy. If you remove 1 point from a sphere, then it becomes contractible. If you remove more than 1 point from a D sphere, it becomes a wedge of D minus 1 spheres. That's all. So, and I represent this kind of phenomenon by saying that every simplicial D sphere is once complementary D minus one cyclic. Right. And of course, there are many non-polyhedral or non-simplicial examples of R complementary D acyclic complexes. For example, this picture shows one complementary, one acyclic, non-polyhedral two sphere. Okay. Right. So now let me state the main theorem. Okay, suppose you have an R minus one complementary D times R minus one cyclic regular CW complex X. And we assume that R is a prime power. Then for any continuous map F from X to RD, there are pairwise disjoint faces sigma 1 to sigma R of X, such that their images intersect. So the topological Tverbergs theorem is the case where X is D R minus one times D plus one simplex. Yes. All right. But it might be suspicious that this is really a generalization of a Tverbergs theorem. I mean, there is no proper examples generalizing the Tverbergs theorem. You may, but actually there is. I mean, so let's consider the case R being 2 and X being a simplicial sphere. So it's the corollary. It's this corollary. I mean, let X be a simplicial D sphere. Then for any continuous map from X into RD, there are disjoint faces sigma 1 and sigma 2 of X such that their images by F intersect. And we already know that every simplicial sphere, every simplicial D sphere is one complementary D minus one cyclic. So we can apply this corollary to we can apply our main theorem to a D sphere, simplicial D sphere, to get this corollary. And this corollary shows that our main theorem is a real generalization of the topological Tverbergs theorem, because not every simplicial sphere is the boundary of a polytope, and which is an old result of Grunbaum. Okay. So this corollary is also considered as the somewhat Borsuk-Ulam theorem with combinatorial flavor. Okay. All right. Any questions so far? All right. So let's see. Let's look at the outline of the proof. The proof uses a so-called topological method in combinatorics. Here is the outline. So the first step is to construct a space X. Construct a space C from a given space X, and we show that there is a sigma R action on C. Sigma R is the symmetric grouping R letters. The second step is this. If the statement of the main theorem does not hold, then we can construct a sigma R map from our C into D, where D is homotopy equivalent to the D times R minus one sphere. So, and the third step is to show the contradiction from the existence of such a sigma R map. And we use the Borsuk-Ulam theorem or its generalization to get such a contradiction. This is the outline. Okay, so let's start with constructing a space C from a space X. It's actually a combinatorial version of the configuration space of points in a space. Okay, so let f of xr denotes the configuration space of our points in X, ordered configuration. So one of the fundamental tools to study this configuration space is the Fadell-Neuwirth the fibration for X, for a manifold X. I mean, fxr is a subspace of X to the R. So we have a map pi from fxr to X, which is the restriction of the R projection. And if X is a connected manifold, this map is actually a fibration. This is very nice, but in our situation, this is useless because we are not considering a manifold. X is just a regular CW complex. And actually, the fiber of pi is the f of x minus xr minus 1. And this configuration space changes drastically as X changes if X is not a manifold. But our combinatorial version of a configuration space, this projection pi behaves very well. Okay, let's introduce the combinatorial version of the configuration space. And let X be a regular CW complex. And then the discretized configuration space of X, say, denoted conf Rx, is a subspace of X to the R, consisting of faces sigma 1 times dots times sigma R, such that these sigma i's are pairwise disjoint. Okay, so the continuous version of the usual configuration space is a complement of the braid arrangements in X to the R, and the discretized version is the complement of the braid arrangement with its neighborhood. Okay. All right. So, and we let delta denote the diagonal set of RD to the R. Then we have this lemma. Let F be a map from X to the RD such that every pairwise disjoint R faces of X do not intersect if they are mapped by F. Then there is a sigma R equivariant map from conf Rx to the complement of delta. This is the map is just a restriction of the product of F. I mean, the map from X to the R to RD to the R obtained from X. This is a point. Okay. Right. So now we apply this generalization of the Borsuk-Ulam theorem by Dot to this map. Right. So Dot proved that for any non-trivial finite group and free G complexes X, Y, if there is a G map from X to Y, then the acyclicity of X is less than the homotopy dimension of Y. So if G is the cyclic group of order 2, this is the usual, this is a slight degeneration of the Borsuk-Ulam theorem. But this holds for any non-trivial finite group. Okay, so how to use it? Okay, so the answer is this lemma. If conf X is D times R minus 1 cyclic, then for any continuous map F from X to RD, there are pairwise disjoint faces sigma 1 to sigma R, whose images by F intersect. This is obtained by this Borsuk-Ulam theorem applied to the map in yellow. Okay, so because RD to the R minus delta is homotopy equivalent to this sphere. Okay, and when R is a prime, then Z mod R in sigma R acts freely on conf X. So we have a map. So I mean, if R is a prime, this map in yellow is a ZR map, and ZR acts freely on sources and source and the target spaces. But we are assuming that the configuration space has a cyclicity like this. It's impossible. Okay. And if R is a prime power, we can't apply the Dot theorem because the action of ZR is not free. But a little bit of an easy computation of the equivalent cohomology, we can prove the non-existence of and sigma ZR equivalent map from conf X into the RD to the R minus delta. So it's essentially the same. Right. Okay, so it remains to prove, or it remains to compute the acyclicity of the discretized configuration space from the data of X. Actually, this is the main point of this talk. As I told you, that the Faddeev-Neuhaus vibration doesn't behave. Faddeev-Neuhaus map doesn't behave well for non-manifold, but if we consider the discretized configuration space, it behaves very well. Yeah, like this. Okay, so let's see the behavior. Okay, first, let pi be a map from conf X to Rx, which is the restriction of the Rth projection of X to the R onto X. And if a point small x of X belongs to the interior of a face sigma, then its fiber is conf R minus 1 of X of sigma. So the fiber depends on its location in X. But we have a very good, these fibers behave very nicely like this. As X in the boundary face tau of sigma moves into the interior of sigma, then the fiber changes by the inclusion conf r minus 1 of X sigma into conf r minus 1 of X tau. Because tau is a face of sigma, X of sigma is a subcomplex of X tau. So we have this inclusion. So this shows that conf Rx is obtained by gluing sigma cross conf R minus 1x sigma. Okay, this actually means that conf Rx is a homotopy colimit of some functor. Okay, let's define a functor. Let P of X denote the face poset of X. And we assume this poset as a, we understand the poset as a category in the usual way. Then we can define a functor fr from Px to top by setting fr sigma to be conf r minus 1x sigma. And the induced map by the inclusion. Then we can define, then we get a functor fr. And actually, the observation we made in this slide, I mean, conf Rx is obtained by gluing these spaces. This means that conf Rx is a colim of fr. Now we have we get a Hokolim expression of the conf Rx, then we can compute its acyclicity by the Bausfield conspectral sequence. Now actually, we are considering a poset, a functor over a poset, then the Bausfield conspectral sequence becomes very easy. I mean, there is a spectrum for any functor f from Px to top, there is a spectral sequence like this, which computes the homology of Hokolim F. Right. So now, by this spectral sequence, we get this lemma. Let f be a functor from Px to top, and if sigma is n minus dimension sigma cyclic for any sigma in Px with dimension less than or equal to n plus 1, then the homology of Hokolim F is isomorphic to the homology of X in dimension less than or equal to n. This is very easy because in the E1 term of the spectral sequence, the assumptions, this assumption says that this part consists of only 0. So the homology of Hokolim F is isomorphic to the homology of the 0th line. And the homology of the 0th line is nothing but the homology of X. Right. So with this lemma, we can compute the cyclicity of conf Rx like this. If X is R minus 1 complementary and acyclic, then conf Rx is n acyclic. This is done by induction on R. The first step is trivial because conf 1x is X, which is n acyclic by assumption. And suppose conf R minus 1x is an acyclic, then by assumption, x sigma is R minus 2 complementary n minus dimension sigma cycle. Then we can apply the lemma to get this isomorphism. And since x is an acyclic, we get that conf Rx is an acyclic. All right, so the definition of the n R minus 1 complementary and acyclic complexes is just is to guarantee that we don't have to compute the spectral sequence actually. So I think you can find a better condition to get the homology or acyclicity of conf Rx instead of the R minus 1 complementary and acyclic complexes. But this is just a first step. Okay, so this completes the proof of the main theorem. And I have some time. Okay, so there are some possible future directions. We have used the discretized configuration space to prove the Tverberg's theorem. And the key is its acyclicity. And the acyclicity is used to apply the Borsuk-Ulam type theorem. So, and actually there are many invariants which are used to apply the Borsuk-Ulam theorem instead of acyclicity or connectivity. One of them is the index. Okay, so let's recall the definition of the index. Okay, let G be a finite group. Then the index of a free G space X denoted index is the LS category of the natural map from X mod G into BG. A natural map means the classified map. All right. So we can easily see this lemma. Let G be a non-trivial finite group. Then for free G spaces X, Y, if there is a G map from X to Y, then in the X is bounded above by in Y. Because this is obtained just by composing map induced on the orbit space. Okay, the second is this. For any free G complex X, there are inequalities like this. Acyclicity of X is less than index, which is less than or equal to the homotopy dimension of X. All right. And we, in this talk, we only used these two invariants to apply the Borsuk-Ulam type theorem. But index is better than acyclicity. So we can replace, if we replace acyclicity with the index, we get a better result. Or I mean, we get a Tverberg's theorem for wider class of CW complexes. Okay, so let me end my talk by posing two problems. Okay, so as I told you, in conf Rx, with respect to the free ZR action for R prime, would generalize our result. So there are two natural problems arising from this observation. The first one is this: compute the index of conf Rx for R prime. The second one is this. Of course, the index of conf Rx is bounded by its LS category. And the LS category of conf Rx is of independent interest, I think. So the second problem is this. compute its LS category. And if you can compute the LS category, it's natural to think about the TC. So you can also compute the topological complexity of the discretized configuration space. And actually, these problems for the usual configuration spaces are very old. Actually, it was probably posed by Fadel or Hussein, one of them. And in the usual topological case, these problems are very hard, actually. But in the discrete case, and if you restrict X to be some class of simplicial complex, you have chance to get answers to these problems. Okay, that's all. Thanks very much.
Well, every one of you would unmute your microphones and we can thank Daisuke again. Very good. Are there any questions? Anything? I actually have one comment. If you would go back one slide. This index of the free G space, at least in the case when X is simply connected, the LS category of the natural map of that map that map is the classifying map for the universal cover then. And so that category is the sectional category of the universal cover. And
yes.
Schwarz had a theorem that said that's something called cat sub 1. So there are things known about this index which might fit into this problem.
Yes, thanks. Yes, and of course this index is closely related to pi 1 category of something.
Well, that's what cat 1 is basically.
Okay.
Yes, same thing. That's right. Anything else?
Well, just to add to that, if X is not simply connected, then I think this is still going to be the sectional category of the map from X down to X mod G, just the quotient map by the action.
Mm-hmm.
So you can still sort of try to use the nilpotency of the kernel in cohomology and these kinds of methods.
Yeah, that's exactly right.
I have a question actually about the condition in the main theorem, which I can't R-1 complementary something acyclic. I mean, are these things all homology manifolds?
Sorry, homology manifold?
Yeah, so that you said they're all generally will not be non-manifolds.
Mm-hmm.
The regular CW complex X, which is R-1 complementary.
It's just a regular CW complex, not homology manifold. I mean, I meant that the Fadel-Newworth fibrations only works for manifold, but we are not using that, so we don't have that.
I guess I didn't fully internalize the condition that you're using, but I thought maybe it would imply that it's a homology manifold, even if it's not a manifold, but maybe I'm wrong.
Sorry, are you talking about this theorem?
I'm talking about your main theorem and the assumptions placed on X.
Oh, I see.
Mark, do you mean that somehow it should satisfy Poincare duality of some type?
I mean that like the local homology is the same as that of a manifold because, so could you go back to the definition then of R-1 complementary? Yeah, so if you take K to be 1,
mm-hmm.
You're sort of removing one face and saying that, you know, it's almost got the homology of a point. Yeah, I'd have to think about it and
Nice.
remind
Yeah,
myself of
it's-
the definition.
It's complicated actually.
Okay, it's more
I also
complicated.
have a question. I really like this construction of this combinatorial Fadel-Norwood vibration. Very nice. And there can be also, I mean, there is also a combinatorial version of Totaro spectral sequence for this, this combinatorial approach. And also you mentioned at the end a few questions. There can be, you can add to this a question about parameterized topological complexity when you look at this, well, your configuration space, well, discrete configuration space and its projection onto, well, this kind of this combinatorial Fadel-Norwood bundle. I think it would be very interesting also.
Okay, thanks. Thank you.
I have a question. Thank you very much, Daisuke, for the nice talk. My question is about also about these discretized configuration spaces. It is quite interesting that these spaces have just the right topology to understand these kind of combinatorial questions, of course. But this is a sort of a tangential question, namely, what is the relationship to these combinatorial configuration spaces to the regular configuration spaces? Namely, in the case, let me just make one point, an extra point. In the case when X is a graph, if the graph is highly subdivided, essentially, but you get that they have the same homotopy type because of a result of Abrams. This is just Abrams's model. So I was wondering whether more generally, if X is not necessarily of dimension 1, you have a homotopy equivalent. It will not be obviously in general, but some kind of a condition that assures that you have the same homotopy type.
I think if you subdivide the complex enough, then they have the same homotopy type, I think. Probably it can be shown by using the Daitamaki's cellular stratified space or something like that. Probably you know better. But yes, that's a good question. But for our purpose, many cells are not interesting, because if you have many cells, we have Tverberg's theorem gets easier because there are many choices of faces, pairwise disjoint faces. But in a general situation, I think many cells give you some moderate treatment of the discretized configuration space. But I don't know how many times you have to subdivide, but
in the case of graphs, there is a very explicit condition about traveling between essential vertices, essentially. And I was wondering whether there is an analog for more general complexes.
Yes, at least the regular CW complex, there is, I think, because they are controlled by its phase poset, and the situation is almost the same as graphs.
All right, thank you.
Any other questions? Okay, if not, I'm going to stop the recording now.